Alright, what's up guys? In this video we're going to do a little bit of vector calculus and we're going to be talking about flux today. So the question that we have today says find out what flux of the vector field F across the boundary of the analogous R, which is which when expressed in polar coordinates is set to R comma theta, where R is in between 1 and 2 and theta is in between 0 and 2 pi. Alright, so we're calculating flux here, outward flux. So we're going to use Green's theorem, the flux form of it. Because remember, there's two types. There's two parts to Green's theorem. Green's theorem has the circulation form and then the flux form. So we're going to use the flux form here to calculate the flux. Okay, so I don't want to run out of room, so I just kind of like write it down here. So this is Green's theorem, the flux form of it. I'll explain what everything means in a moment. We'll just kind of get everything written down. Look at the double integral, so region, that's the R stands for. And the partial of f with respect to x plus the partial of g with respect to y, and then dA. So that is the flux form of Green's theorem. Now we're going to use this to find the flux. Okay. So the best thing to do is to identify what f is and what g is. So if we identify what f is, we're given the vector field. Let me write the vector field back down here because it is kind of up there, and you might not be able to see it. So this is our vector field that they gave us up on top, and we just simply need to identify what f is and what g is. By the way, in the formula, this here represents the outward flux. Just kind of wanted to write that down for you guys to see. Alright, so you got the vector field. So let's identify what f is and what g is. So f is obviously going to be the xy squared, and then the g is just going to be the x squared y. Okay. So if we set it up, and we'll take the partials in a moment. Or maybe I should do that. No, I'm going to set it up first, because I kind of want you guys to see what's going on before I do all that. I'll take the partials in just a moment. Just kind of want to write everything down first. And I think it'll be crucial too, so that way you can see what you need to, how you need to differentiate it, or partial differentiate it. Okay, so that's what you'll have. So what we need to do is we need to take the partial of f with respect to x. And so we just look at f here, we take the partial with respect to x, right? You just end up getting y squared. Then, according to Green's theorem, we need to take the partial with respect to y. Hold on guys, give me 1 second. Sorry, my cat keeps attacking my foot while I'm trying to do this video. Okay, so yeah, we took the partial of f with respect to x, so we took care of that. Now we need to take the partial of g with respect to y. And you can see kind of how this is working a little bit. So we'll do that. We're using Green's theorem, remember? So if we look at g here, and we take the partial of g with respect to y, Well, we'll just get x squared, because you have to take those partial derivatives. Now we set up the double integral. R is the region. We have y squared plus x squared. We got dA. Now remember, they did give us it expressed in polar coordinates up here at the top. Hope you guys remember when I went over that at the beginning. So this would be x squared plus y squared is equal to r squared, if you remember that. And we would just end up turning it into polar coordinates. So it'd be the double integral from 0 to 2 pi. We got all this information up here at the top. And then if we look up here at the top, the next limits of integration will be from 1 to 2. And then this becomes r squared times r, and then it's going to be dr d theta. That's how we're going to evaluate it. So what we do here, or what you can do here to make things a little bit easier if you want to, actually I should have done that at the beginning, or when I first started, just to save a step. But I'm going to multiply r squared and r, that give me r cubed. So this won't change. This will be from 0 to 2 pi, and then this will be from 1 to 2. And then this will just be r cubed, and we integrate that with respect to r, and then with respect to theta. This is in polar coordinates. All right, so we need to respect to r first, treating theta as a constant, work from the innermost integral to the outermost one, which is here. So until you get the hang of the process, break it up. So clearly, this just becomes r to the 4th over 4, evaluated from 1 to 2. You plug the 2 in, and then you plug in the 1 after that. 2 to the 4th is 16. I know that because 2 to the 8th is, 2 to the 3rd is 8, so that means that 2 to the 4th is 16. But if I divide 16 and 4, I'll get 4. And then this would just be minus 1/4, right? 4 minus 1/4, that's 15 over 4. We then take this 15 over 4 here, and we integrate that with respect to theta, because we're integrating a constant basically. So this will be from 0 to 2 pi, and then we'll have 15. This is super easy because we're just integrating constant. And we're integrating this time with respect to theta. And so obviously, if we're integrating with respect to theta, this would be 15 over 4 multiplied by theta, evaluated from 0 to 2 pi. The 2 pi gets subbed in first, and then you sub in the 0 after that. So if you sub in the 2 pi, well, it just kind of reduces a little bit. So this actually just reduced down to 15 pi over 2. And if you sub in 0, you get 0. So that'll be 15 pi over 2 minus 0, which is just 15 pi over 2. And that's your final answer. So as you can see, we use Green's theorem over at the top to calculate the flux. Again, you want to make sure you pay attention to the question, because there's the circulation form of Green's theorem and the flux form. So you want to make sure you're using the correct form. So you go through, you take your partials, which we did. You go through, we had to convert it, express it in polar coordinates as they mentioned up at the top, which I did here. We set up the double integral based on the information that we were given. We used our vector field to take our partials, and that's pretty much all there is to it. All right, so if y'all have any questions, let me know. I'm going to be posting another video here in a moment, doing another example of a surface integral. So if you want to see that, feel free to join in. If not, it'll be posted. I'll see y'all next time.